You've probably done it. You type a password. It fails. You try a variation. It fails again. Now you're guessing, not computing. Here's a thought experiment that looks boring, but it's the cleanest doorway into quantum computing. There's one secret number hidden in a list from 0 to n-1. You have a black box checker. Give it a number. It answers yes for the secret, no for every other. No hints, no shortcuts, just yes or no. On a normal computer, the best strategy is still guess and check. On average, you need about half the list. That's O of n. Now for the myth. A lot of people hear quantum computer and assume put every number into a superposition, check them all in parallel, and the answer pops out. That picture creates one dangerous intuition, that the quantum computer did all the work, and you get to read it all. You don't. When you read a quantum computer, you get one outcome, one sample, not a list, not a screenshot of parallel universes. One result, drawn at random. So here's the quiz. In a quantum computer, how many checks do you need to find the secret number? Not O of 1, not O of log n. The best possible is O of square root of n. And this isn't just a clever trick, it's the limit. Researchers proved you can't do better than square root of n in this black box setting. So Grover is not one algorithm. It's the best you can ever hope for. If the list has 1 million options, a classical search averages about 500,000 checks. A quantum search needs on the order of 1,000. That's a real speed up. But it's not magic. The algorithm that achieves this is Grover's algorithm. And it's the most honest way to explain what quantum computing is. Because Grover doesn't hide behind metaphors. It puts the weirdness on the table. Here's the minimal idea you need. A classical computer stores a definite state. A bit is either 0 or 1. A register is a specific string of zeros and ones. A quantum computer stores a state vector. Think of it as a list of amplitudes. One amplitude for every possible bit string you could read out. If you have k qubits, there are 2 to the k possible bit strings. So the state vector has 2 to the k components. A qubit is the smallest case. It's a 2-number state. 1 number for leaning towards 0. 1 number for leaning toward 1. When you measure, you get either 0 or 1, randomly, and then the state collapses onto what you saw. Now, the rule that feels backwards, you don't treat amplitudes as probabilities. You square their magnitudes to get probabilities. So if one amplitude has magnitude 1/2, its probability is 1/4. If an amplitude is negative, the probability is the same. But the state is different. And that difference is the engine. If you want one concrete analogy, use sound. Think of 2 speakers playing the same note. If one is flipped in phase, the sound can cancel in parts of the room. Nothing mystical happened. Waves just added and subtracted. Quantum amplitudes behave like that. They add, they cancel, they reinforce. A quantum program doesn't directly compute an answer. It sculpts a probability distribution. It rotates and reflects this invisible state vector so that the right output becomes very likely. Then you measure. And measurement gives you one classical output, randomly, according to those squared magnitudes. That's why doing everything in parallel is misleading. Parallel work you can't read is not power. Power is the ability to steer the odds. Quantum gates are the steering wheel. They are operations that rotate and reflect the state vector. They must preserve its total length, so the math is geometric. One gate matters a lot for Grover, the Hadamard gate. Applied to a qubit that starts as a definite 0, it creates a 50-50 balance between 0 and 1. Applied to all qubits, it creates an equal balance over every possible bit string. So Grover starts by spreading probability evenly. Every candidate key is equally likely. If you measured right there, you just get a random guess. Useless. So Grover adds a second ingredient, a mark. You're given that black box checker, the oracle. In practice, the oracle comes from your ability to verify a solution quickly. If you can build a classical circuit that checks a candidate and outputs true or false, there's a standard way to turn that checker into a quantum circuit. The quantum version doesn't reveal the answer, it just marks it. And marking means this: if the input is not the secret, do nothing. If the input is the secret, flip the sign of its amplitude. That's it. A phase flip, a minus sign. Still no probability change, because squaring erases the sign. So why does this help? Because Grover pairs that invisible minus sign with a second reflection, a reflection about the equal balance direction. People call this the diffusion step. Some call it inversion about the mean. Here's what it does in plain language. It takes amplitudes that are below the average and pushes them above. And it takes amplitudes that are above the average and pulls them below in a perfectly symmetric way. Let's make that concrete with the tiniest non-trivial example. 2 qubits, 4 possible outputs, start with equal balance. Each state has amplitude 1/2, so each has probability 1/4. Now suppose the secret is the state 11, and by mean the oracle flips its sign. So now the amplitudes are 1/2, 1/2, 1/2, and -1/2. The average of those 4 amplitudes is 1/4. Diffusion reflects each amplitude around that average. A reflection around a value means new amplitude equals 2 times the average, minus the old amplitude. So the 3 non-secret states go from 1/2 to 2 times 1/4 minus 1/2, which is 0. And the secret state goes from -1/2 to 2 times 1/4 minus -1/2, which is 1. Now look at the probabilities. The secret has amplitude 1, so probability 1. The others have amplitude 0, so probability 0. In this toy case, Grover finds the answer in 1 round. That doesn't happen for large n, but the mechanism is the same. The sign flip makes the secret below average. Diffusion turns below average into above average, and repetition keeps pumping amplitude into the secret. This is the real quantum trick, not try every answer. It's use interference to pump probability into one answer. Now the beautiful part, even though the state vector lives in a space with 2 to the k dimensions, Grover's algorithm only moves inside a 2-dimensional slice. One axis is the secret state, the other axis is everything else, averaged together. Inside that slice, the oracle is a reflection, the diffusion step is a reflection, and 2 reflections equal a rotation. So each Grover iteration rotates the state vector by a fixed angle toward the secret. What's the angle? If there are n possibilities, the equal balance state has amplitude 1 over the square root of n on every option. So its overlap with the secret direction is 1 over the square root of n. That means the initial angle away from not the secret is tiny, about 1 over the square root of n in radians when n is large. Each iteration rotates by about twice that tiny angle, so you need about 1 over that angle many iterations to get close to the secret. That's square root of n. More precisely, the best stopping point is about pi divided by 4 times square root of n. That's where the famous constant pi over 4 comes from. It's literally the quarter turn showing up in the geometry. So with 1 million options, square root is 1000. Pi over 4 times 1000 is about 785. After about 785 iterations, the secret outcome becomes overwhelmingly likely. Then you measure once, and you almost surely read the secret. Almost, not always. And here's another counterintuitive twist. If you keep running Grover iterations forever, you don't keep improving. You overshoot. The probability swings back down, because you're rotating on a circle in that 2-dimensional slice. So Grover has timing. There's a sweet spot. Measure too early, and you might miss. Measure too late, and you might rotate past peak probability. Now, why does this matter in the real world? Because Grover is not a database search tool. It's a general speed-up for any brute force style search where you can verify a guess fast. That includes parts of cryptography. Here's the practical headline. Grover turns a brute force search over n possibilities into about the square root of n oracle calls. For symmetric keys, that means the effective security level is roughly cut in half. A key space of 2 to the 128 becomes about 2 to the 64 steps under Grover. 2 to the 256 becomes about 2 to the 128. That's why the modern response is not panic, it's migration and key sizing. Standards bodies have already been moving. For example, NIST finalised its first post-quantum cryptography standards in August of 2024. That's the world preparing for the long game. But here's the equally important reality check. Grover's algorithm assumes you can run a long, precise quantum circuit. Each iteration is not free. The oracle can be enormous, and today's quantum hardware is noisy, so the bottleneck is often not the square root math. It's whether you can do hundreds or thousands of clean iterations without errors washing out the interference pattern. That's why the biggest milestones in the last couple of years have been about error correction. Google has highlighted error correction progress with its Willow chip in December of 2024. IBM's public roadmaps emphasize circuit capability, not just raw qubit counts, including a 120 qubit processor called Nighthawk on its 2025 roadmap, and a fault-tolerant system target called Starling around 2029. Those names matter less than the idea. The future is measured in logical qubits and circuit depth, not just physical qubits. Now for the best reveal, the thing most people never get told. Grover's algorithm isn't only about finding a needle. It's a reusable pattern called amplitude amplification. If you have any quantum procedure that produces the right answer with a small probability, Grover-style reflections can amplify that success probability. You pay about the square root of the inverse of that probability, and you turn rare success into likely success. That's bigger than search. It's a way to make quantum randomness act like a reliable lever. One last practical piece. Grover is the perfect lie detector for quantum hype. If someone claims quantum search will make everything instant, ask 4 questions. First, what is the oracle? What exactly is being checked, and how expensive is that check as a circuit? Second, how many iterations are required? Square root helps, but square root of enormous numbers is still enormous. Third, how much noise can the machine tolerate? Grover's advantage comes from tiny, repeated rotations. If errors randomly bump the vector off course, the careful build-up disappears. Fourth, what is the success probability at the end? Grover gives high probability, not absolute certainty. So you still verify, and sometimes you rerun. Also, a small honesty note. In full quantum mechanics, amplitudes can be complex numbers, not just positive and negative reals. That complex part is how phase becomes richer than a simple minus sign. Grover, mercifully, can be explained with just plus and minus, but many other quantum algorithms lean heavily on complex phase. So if you take nothing else from this video, take this. Quantum computing is not parallel answers. It's controlled interference. Grover is the simplest proof that interference can beat brute force. And once you see it, the field stops looking like science fiction. It starts looking like math you can test, hardware you can measure, and claims you can judge with clear questions. So the next time you hear, quantum computers try every key at once, translate it. A quantum computer can't read every key. It can only ask yes or no questions through an oracle. What it can do is reweight the entire search space with interference, so each question buys you more progress than a classical step. That's Grover's algorithm, and that's the simplest, honest definition of quantum computing. A machine that computes by sculpting probability with interference, then takes one sample from the result. If you understand that, you're ready for everything else. Shor's algorithm, quantum simulation,